Assignment, last assignment is out. It's due on December the 2nd. It should be reasonably straightforward. It's much more like exam questions. There's no programming. There's a few modeling questions and answering and playing. So I want you, it's one of these learning by playing assignments. I want you to play with things and tell us what you found is the idea. There is a solution to assignment 3 available. And does anyone have any questions about anything? All right. So what we've done so far is we've talked about probability defined in terms of measures over possible worlds. The probability of a proposition, the measure of the propositions in the world, is the measure of the set of worlds in which the proposition is true. We condition on evidence. You make the worlds incompatible with the evidence, have measure 0 and renormalize. And so this way of viewing it told us how to do it in variable elimination. All we did was just cut out those. We just ruled out those values in the tables that were incompatible with our evidence. And then we have this belief networks. Each variable is independent of its predecessors given its parents. And then a factor is a function from a set of variables into the real numbers. And then we did this, the end of last time, we're doing this variable elimination algorithm, computing some variable given some evidence. We constructed a factor for each conditional probability table. We set the observed variables to their observed values, so each one, whenever the variable had a value, any factor that contained a variable that was observed, we just selected those particular, the tuples in the factor which are consistent with the observations, or equivalently, we just made the other ones 0. And then we summed out each of the variables according to elimination ordering. And then we ended up with just factors on the query variable z here. We multiplied them, and then we renormalized. Okay, are there any questions about that? That's what we did last time. Okay. So let's do some clicker questions, and we'll make sure this works. My other computer's in the getting fixed up, so I have an old computer. I'm not sure I can. All right. So looking at this belief network, W leads to X, leads to Y, leads to Z. The question is, which probabilities does it require to be specified? What do you have to specify to do this? It's not designed to be tricky. It's designed to lead you into and how are we going? Does anyone need more time? Does anyone need more time here? Okay, let's stop that. Where am I? Right, so the answer is B. The answer here is B. Whoops. So where there seems to be 20% of the people who are not doing it. So D is the other way around. Its variables go into the parents. So this is W, and X has a parent of W. So it's X given W, not W given X. Okay, you have to, because we're going to see lots of examples like this soon. Okay, any questions about that? All right. Next question. The belief network. Same belief network. Which factors are created in variable elimination? What are the factors we're creating on? Okay, do anyone need more time? Do you want to do more time? Okay, 3, 2, 1. Oh, we'll stop. We'll show it. Oh! That's interesting. It's the same question as the previous one. Oh. It's the same question as the previous one. We need this factor on W. Oh. This is why I want to like this test. We have P of W. We have P of X given W. We have P of Y given X. We have the probability of Z given Y. And these ones go into the same factors. Some factor of W, some factor of W and X, some factor of X and Y, and some factor of Y and Z. Right, each one of these just becomes a factor. So the answer here is again B. Any questions about that? Let's move this away. I don't know how to move it. So the answer here is B. People said C. Right, and there's a factor on W. So C is not right, we need this one. What do people say is D? No, D's the other way around. It's the same as before. It's the same question as before. And you got that one, so you should get this one. Any questions on that? Any questions? So each one of these is just maps across to a factor. All right, next question. Whoa. Now we're just going to look at those factors. So now you know where these factors came from. It's the f of W, Wx, xy, and yz. Now I want to ask the question, if variable x is eliminated, which factors are multiplied? So if variable x is summed out first, which factors are multiplied when summing out x? So what are we going to multiply? All right, how are we going here? Do we need more time? More time. Yes. F1 and F2. We're going to multiply F1 and F2 together. Right? We're not going to multiply F0. F0 doesn't, so C is wrong. We're not going to multiply F0. F0 doesn't contain X. So it's only those variables that contain X we're going to multiply together. Okay. Same question. So now we're going to sum out Z. Which factors are multiplied when summing out Z? How are we going? Does anyone need more time? Anyone need more time? 3, 2, 1, we'll stop. None of them, good. Don't need to multiply any factors, we're just going to sum out Z. Okay, the only ones that we don't want to multiply, just the ones that contain Z is the only ones we're going to do. All right. In variable elimination, the same factors, we're now going to eliminate x. Which factors remain after summing out x? So what's the result of summing out x? A set of factors, which that's what ATV4. Okay, anyone need more time? Still, let's stop. 3, 2, 1. We'll stop. Yes. Yay, everyone, people know how it works. Good. All right, so if you know this, you know how variable elimination works, right? So most people do. Few people are still. You get rid of, C is not right, you get rid of F1 and F2 when you eliminate them. Right, they no longer exist, you've got rid of them. And B is, well, you don't multiply F0. Okay, any questions about that? And we'll do last one. We're eliminating Z. All right. All right, do you need more? Anyone need more time? We're getting there. Okay, 3, 2, 1, stop. All right, perfect. Okay, the answer is B. Some people said E. No, we get rid of F3 because we're summing out Z. Once we got rid of Z, we don't have that. Okay, are there any questions about that? So now I'm going to assume you know how to do variable elimination. Now we're just going to start modeling things. Okay. Any questions about that? All right. So what we're going to do is we're going to finish off talking about variable elimination because we're going to talk about pruning networks based on evidence in a query, and that should take us about 3 minutes. We're going to talk about causal models and non-causal models. We're going to try and distinguish them. Then we're going to talk about, so we'll learn about how marijuana leads to hard drugs or not. Then we'll talk about how Microsoft Help System works, or the original one did, based on what's called a naive Bayesian classifier. And we'll talk a little bit about how to learn probabilities from data. Okay. So if we want to compute the probability of leaving, what variables can be pruned? What's sort of irrelevant to us? So is there anything that's irrelevant that we don't need to care about? Yeah. Right, you don't need to care about RE. In fact, if you sum over RE, what do you get? Yes, so if you get the probability of RE given leaving, and you sum out RE, you get 1 everywhere. What else can you do? What else can you remove? Smoke. You can also remove smoke. Right? You can remove smoking and report. What if you want the probability of fire given smoking? What can be pruned? We've observed smoke. We want the probability there's fire. What can be pruned? You can move everything except for fire and smoke. Right, we can prune report. for the same reason we could before. And once we've pruned report, we can reprune leaving. Once we've pruned leaving, we can prune alarm. Once we've pruned alarm, we can prune tampering. Okay? So in particular, the general rule is you can prune any variable that's not queried, is not observed, and has no children. So if you can prune, so if we're not observing or querying report, we can prune it. If we're not observing or querying smoke, we can prune it. We said repeatedly there, because once we removed report, leaving now has no children, so we can prune leaving. Okay? So when you get that interface and play with it, it's going to say, do you want to prune irrelevant variables? These are the variables it's going to prune. Okay, any questions about that? Good. Because that was just sort of the end, because I want you to play, part of the assignment is to actually play with the applet, and it prunes irrelevant, and asks to prune irrelevant variables, and now you know what it does. All right. So what I'm going to do now is we're going to talk about causality first. So we're going to model this little domain here. So I'm going to think about something called a causal model. And my variables are shoes wet after walking on grass, sprinkler, grass is wet, rained last night, and the grass is shiny, and I'm going to sort of try and draw a reasonably natural belief network for this. So one of the ways of doing this is you want to think about how the world works, and you want to say, well, how are the shoes wet? Well, the shoes are wet sort of depends on the grass is wet, right? So the shoes is wet. And typically you think about how the world works as its grass is wet. And the grass is wet depends on the sprinkler. Right, if the sprinkler was on, then the grass would be wet. But also if it rained, the grass would be wet, right? Rained. And we don't think the shoes are wet doesn't directly depend on rain. It only depends on because the grass is wet is what this model says. And the grass is shiny doesn't depend on whether it's wet. So the grass is shiny. So that's a sort of network that would build. Okay, any questions about that? So now let's suppose, you can run it there. That's the network. So now I can suppose that what if we didn't know the season? What if we didn't know the season? Maybe someone say, well, these two, rained and sprinkler, are dependent on each other because, in winter we tend not to have the sprinkler on. It tends to rain more. So we don't have it in the rainy season. So what we're going to do then is we're going to think about in here, we're going to think about the dependence on here. We're going to introduce a new variable. So instead of having rained and sprinkler, we're going to say they're dependent. Well, why are they dependent? Well, we want to think about that there might be the season. So we're going to try and think about why they might be dependent. So maybe the season is going to influence why they're dependent. So with this thing here, what we're trying to do is when we have variables in here, we want to know why they're dependent, and we're going to we're essentially going to think of why they're dependent. So it's not the fact that rain causes sprinklers or sprinklers cause rain, but rather there is a variable called season that affects both of them. Okay, and we can run this. And we can run this and, whoops, this one. And we get this, and I can solve this, and I can turn this on, and we end up with this sort of thing, right? So the season is winter, the season's 50-50. If we change the season to be make observation, if we take this observation to be winter, then it's unlikely the sprinkler is on, but it's likely the rained, so it's likely the grass is wet. If we changed it to summer, then it's then it's more likely it didn't rain, but it's more likely the sprinkler was on. And so still the grass is wet 50-50. Okay, we're just modeling the dependence on here. So you should be able to and if you don't know the season, right, then there's a lower chance of the sprinkler, but still, it's more likely that it rained. Okay, any questions about that? Good. So that's all stuff that we've seen before. Yes. So now the question is, no one know, suppose we, oops. So what we're going to do is we're going to talk about causality in here. So an intervention, so we're going to talk about an intervention on a variable, actually changing the world by doing things. We're interested in robots and agents and actually acting in the world. And we're going to have this thing called a causal model is a directed model which predicts the effects of interventions. So we're going to have a causal model predicts the effects of an intervention in what we're doing. The parents of a node are going to be what causes something directly. So I'm going to argue that this is essentially a causal model because grass is wet, is what causes the shoes to be wet. The grass is wet, is what causes the grass to be shiny. What causes the grass to be wet? It's either rain or sprinkler. Right? So in some sense, it's a model that obeys this causality assumption that interventions. And we'd expect a causal model to obey the independence assumption of a belief net, because if you knew the direct causes, then everything else is irrelevant. So you'd expect the causal model to obey the belief network, but you wouldn't expect all belief networks are not causal networks because we just chose an arbitrary ordering. Right? So the Bayes net just lets you have an arbitrary ordering and not all of them are causal. Right? The shoes are wet don't cause the grass to wet, and the grass is wet doesn't cause the sprinkler to be on. Right? So in fact, if it's rained and the grass is wet, the sprinkler's not going to go on because the grass is wet. Similarly, the sprinkler is on doesn't cause the grass to be wet, which then causes it to be rained, even though if you're thinking about just dependence and independence, they're all dependent on each other. Okay, does that make sense? So in here, now the question is, which probabilities change if we observe the sprinkler is on? In here, what's the answer? So what's the answer? Which probabilities change if we observe sprinkler is on? All of them. Right, so if we do this. So if we do this, if we observe this, we make the sprinkler on, and we find out that if the sprinkler is on, it's most likely to be summer, therefore it's less likely it rained, therefore the grass is wet. Therefore the grass is more likely wet because it's, the grass is wet because the sprinkler was on, even though it was less likely to rain because it's probably summer. Okay, does that make sense? Now the question is, which probabilities change if we turn the sprinkler on? What happens if we actually turn the sprinkler on? Yeah, so the effect that season and rain are not affected by turning the sprinkler on. So in this causal model, what happens is that when we have a causal model like this, if we turn the sprinkler on, then the season doesn't change. It's only the downstream things that get affected. Okay, so we can start building these models like this. And what happens is, if we intervene on a variable that only affects the descendants, and you can model this by each variable having a new parent, which is force it to be true, and x depends on the other parents if we force is false. An intervention then has a different effect. So we can actually do this in the Bayes net. Actually, I'll just do that. So I can do that in here. I can go to create mode, and I want to really create a parent. I can force the sprinkler on. I can turn the sprinkler on. is another variable. I can make it a parent of sprinkler. Now I can change the probability table so that if I turn the sprinkler on, then the sprinkler is on. And if I don't turn the sprinkler on, it's as it was before. Oh, and I have to make sure that this has the right probability table. And we'll make this, I didn't turn it on. I'm going to make it. I'll ask you a second why I did that. All right, so if we do this now, if we now go to solve mode and look at all these things as well, it actually ends up the same as before. So if we, whoops. So if we go to change the observation to none, right, we end up 50-50 the season. And once, this actually has exactly the same model as we did before. Whoops. I'm going to change this to observe it to be true. And it's the same effect as before. Right, but now, if I don't have this as, change observation as none. If I change it back, if I force it to be true, if I observe this to be true, I'm going to force it to be true, then we didn't change winter and we didn't change rain. Right? So we force this to be true by the way that we understand before how the Bayes net works. This doesn't affect, observing this doesn't affect season, and it doesn't affect rain. And so exactly the same as having it before. So we have a different mechanism that turns the sprinkler on, right, and only affects the children. Does that make sense? Any questions about that? The obvious question is so what's the answer? Why did I make this? Whoops. Why does my prior probability, why did I make it 0.0001? Why did I make that a really small number instead of 0? Yeah. Nothing is certain, but that actually breaks the program. Do you know why? Why does it break the program? Yeah, because you divide by 0. Remember what we did is we divided by the probability of an observation. Right, that's how the system works. It divides by the probability of the observation. If the probability of the observation is 0, it's going to divide by 0 error. Right. I didn't change it here because it's interesting to know why it breaks things. Right. So we really want 0 and 1 because we know whether it's observed or not. But that's why I did that, because I didn't want to divide by 0 error. Okay, any questions about that? All right. Oh, no, I don't want to do that. Okay, so let's play the clicker thing. Let's do some I want to know which of the following, another clicker question. We like clicker questions, they're fun. Which of the following is a causal model? How does the world work? It's sort of an interesting model. I'll explain why this is sort of an interesting model in a second. But which way, to make sure you know, which way does the world work? Is that a causal model between the relationship between lights are on and switches? Is it B? Are both causal models, or is neither? Let's try and think about what that might mean. How are we going? Does anyone need more time? Oh, okay, that's good. 3, 2, 1, we'll stop. Right. So the question is, if I turn the light on, does the switch go up? Or if I turn the switch up, does the light go on? Right, so how do words work? If I have a switch, we don't have switches in here, do we? So if I pull one of these lights down in the house, right, the switch doesn't go on or off. Right, but if I flick the switch, the lights go on and off. And so this one here says that the switch depends on the light. If I move the switch, the light changes. But A says if I turn the light on and off, then the switch goes up and down. Okay, so the answer here is B. It's not, because the way normal lights work, if you change the light, if you pull the light out, you intervene and make it on or off, the switch doesn't go up or down. If you change it so the switch goes up and down, the light goes on and off. And what's interesting about this is, though they're causal models, you can't distinguish these two models by observing the world. Right? There's no observation of the world on which you can distinguish A and B. They actually have this, you can model anything in the world from A and B. They have the same model of the world about how the world works. So you can't distinguish a model that looks like A, B from B if A, from observing the world. And this is why if you take a statistics course, they won't talk about causality because they want us to observe the world. But we actually want to play with the world. And you can distinguish these by playing with the world. You're going to play with A and see whether B changes. You're going to play with B and see if A changes. So if we get to play with the world, you can actually distinguish these two, but you can't just by observing the world. And this is why we need scientific experiments. Because we actually want to play with the world. We want our robots to play with the world. We actually want to carry out an experiment where we're going to change A and we're going to flip B. So here we're going to play with A. When we play with A, we can see if B changes. And here we can play with B and see if A changes. All right, new question. Oh, why did it close? All right, new question. Which of the following is a causal model? If you take marijuana, it leads to taking hard drugs. If you take hard drugs, it leads to marijuana. Are they both, or is it neither? All right, let's go 3, 2, 1. Oh, that's interesting. All right, so what we're going to do is we're going to have something. I'm going to grab this URL. Oh no, I put a copy. Whoops. Copy that. And I'm going to go here, my Java applet, and I'm going to kill this. File, load from URL. And we're going to have a forcing model in here. We're going to model this. And we're going to model this. All right. Here's my model of, here's my stupid model. It's not very realistic. Well, it's so you take marijuana was 0.18, and if you take hard drugs, then it's and if you take hard drugs, if you take marijuana, it's 0.18, but then if you conditioned on given you take hard drugs, it's, let's observe take hard drugs. It's make observation, it's true. It's all of a sudden, in this model, it goes to 57%. It's 0.57. So they're strongly, right? And if you observe that you didn't take it, then it's 0.16. Take hard drugs, 0.16. And now let's look at the other way around. We change it to none. And it's 0.05 and then we're given, you take marijuana, it becomes you can observe that it's true, it becomes 0.15. So out of the people who take marijuana, 15% then take hard drugs, and if you observe this, it becomes to 2. So if you don't take, given not take marijuana, it becomes 0.02. Now, that was all some slow, horrible thing. Now we're going to ask the question, oh, where am I? I want to do this. Make observation to be none. Whoops, I want to make that observation none. I want to know what happens if I force someone to take marijuana. What's going to happen? So what do you expect to happen in the world? What happens in the world if you force people to take marijuana with the effect on hard drugs? What might happen? Or does this say that it has to go up? Does it have to go down? What should happen? I'm being tricky here, by the way. I'm being misleading. I'll tell you in a minute. So I'm going to make force marijuana to be true. I'm going to force it to be true. What's going to happen to... So take marijuana is going to end up being true. What's going to happen to hard drugs? Who thinks hard drugs is going to go up? The probability of hard drugs is going to go up. Who thinks it's going to go down? Right, so we didn't do this. So I'm going to force it to be true, and it was 0.5, and it went down to 0.3. So if you force people to take marijuana according to this model, so if you force marijuana to take marijuana, it goes down, the take hard drugs goes to 0.03. What if you force them not to take marijuana? What happens? If I force them to be false, what's going to happen? You actually know the answer to this. Has to go up. Right, goes to 0.8. So if you force people to not take marijuana, the take hard drugs goes to 0.08. What's happening? There's nothing you haven't seen here. What's happening? Well, right, there are other causes in here. So in fact, this isn't really my model, this is my model. But the fact is, from this observational study, by building a causal model, we can actually work out what's going on. And if you actually look at what's happening here, we'll model this. So we change observation, don't force that, none. Okay. The fact that you take marijuana means that you're drug prone, which then is going to cause, so if you take marijuana, so before they had 11%, if you observe this to be true, want to look at both bad reaction and drug prone, we'll find out that people have a bad reaction. But it's also strong evidence that they're drug prone. And this is why the causal model acts like it is. Right? It's all fiction. But having a causal model lets us explore how the world works. And if you're building experimental design, this is what you want to do. So we want to build experimental design. We want to build these causal models to predict how the world works. And these are really nice models for predicting the model of interventions in the world. Okay, any questions about that? Right, so you can't distinguish. Right, we didn't have enough information before to do this call, but once we have to just have observations of the world, the fact that things are correlated doesn't tell you what happens when you intervene, but these causal models let us build that in. Okay, any questions? Yes? the significance of these arrows here is I'm claiming this is the causal model. It's completely fiction, of course. I just made it up to do it. But this one here says that taking marijuana causes either a bad reaction with your drug code causes you to take marijuana, but whether you take hard drugs is caused by depends directly on whether you're drug prone and whether you have a bad reaction. Oh, that's because they were hidden underneath it. It's the same network. Was this network? I think I click on that one, it goes on top. No, it doesn't. How do I get it on top there? Oh, rats. That's what happened. Yeah, okay. It's because my computer broke and I'm giving me an old one, so hang on. I didn't have a power for it, but I do have another. 2. All right. All right. All right, let's go find where we are here. I knew we'd give out some time. Oh, we're here somewhere. All right, we're going to we did that. All right. So now we're going to give another example of another network, and this is apparently the original version of Microsoft Help System, one stage around 2004, I think, worked like this, because people published about it. They were published, but now they don't tell us how it works. And what it's basically this Bayesian network that has a help page at the top and all of the words at the bottom. And all we're doing here is we have H is the help page that the user is interested in, and at the bottom are all the words that people could use in a query. If you mix up words in a query, you swap them around, it doesn't matter. If you repeated the words, it didn't matter. It's just only the set of words that was used. And what we needed in here, so let's go back here. What do we need? So you know what you need. This is the Bayes net. What probabilities do we need? What probabilities do we need for this Bayes net? What probabilities do we need? No. What do you need? It's a Bayes net. Each variable given its parents, right? What are the variables given its parents? What do we need? It's the same question as the very first clicker question, almost. What do we need? I want you just looking at these things, and then you should know what probabilities you need. That's why it's such a nice model. It tells you exactly what we need. What do we need? What probabilities do we need for this? Yeah. Right. The P of the word given the help page, and what else do we need? Right, so we need this for every word. This for every word. And what else do we need? Come on, it's just a Bayes net. What else do we need? Oh, you guys, if you ever met that looks like this. A, B, what probabilities do we need? We need the, So what probabilities do we need here? As well as this. Right, the probability of H. And H, each of these words is Boolean. It's whether you used it or not. But H is the domain of H is all the words. It's all the help pages. So the domain of H, sorry, we call it the range of H, is the set of all help pages. And there's a prior distribution over how likely people are to have help pages. And each word is Boolean, so each word is Boolean as to whether it's It's true if the word's in the query and it's false otherwise. That's true if the word is in the query, in the user query, and is false otherwise. But the fact that you need these two things just follows from our diagram. That's why there's such nice diagrams. You just draw a diagram and everyone knows what probabilities you need. So once you draw this diagram, we know what probabilities you're going to do. So we're going to have the probability of HI for each help page. For each help page, we're going to say how likely is it a priori that they're going to use it. And we also need the probability of each word given each help page. So it's how likely each word is for each help page. And there can be multiple words in a query, so that's, in fact, this says that the words are independent given the help page. Okay, and given a help query, what do we do? Given someone types in a query, what happens? So what happens when someone types, the user types in a query? Well, you have an observation, right? What do you have observations on? Yeah. Well, no, here they just assume we have the whole words. Right, here we just observe the words. I actually give an example of that later on. We'll give an example of how predictive word typing works, but that's another simple thing. But at the moment, we're just doing this one here. We're just typing in words, and you condition on the words that these users used. So we condition on the words in the query, and it displays the most likely help page. And you know how inference works in this. Each one of these, each time we do this, it ends up with. So if we have able is either true or false. And for each help page, H1, we have some probability, some help page 2, some help page n. Right, and there's some number like 0.01 and 0.3 and 0.01 or something, right? Whoops. And if we observe able is true, all we're going to do is just multiply the help pages by these numbers and renormalize. So it's just a big multiplication of something and then renormalizing. So whenever we get observe able, if we observe this, we just cross this out. We multiply this vector by the probability of H and renormalize at the end. Right? It's our variable elimination. It just told us what to do. Every word they use, we just multiply it by this vector and we renormalize it. That's just, because you know how this works. I don't need to give you another algorithm for this. You know the algorithm for this. Okay. Okay, let's stop now. Next time we'll talk a little bit about how for learning these probabilities, and then we'll start talking about decision making.